Hi, today I will be describing our work titled Adversarially Robust Transfer Learning, which can be useful for training robust models in settings where we have limited training data. Let's start off by giving a very brief introduction to adversarial examples. Given a clean example, for example this cat, that gets classified correctly by a classifier, an adversarial example is an example which looks very similar to the clean example in input space and to any human, but gets misclassified. In this work, we will be focusing on additive and bounded adversarial examples. These additive perturbations are often bounded in some metric, for example an infinity metric, to ensure that they are imperceptible and small. One popular method for training a robust classifier which can resist adversarial examples is adversarial training. Adversarial training can be seen as a constant sum two-player game between an adversary which has access to the delta perturbations, which are, as described earlier, additive and bounded, and the network which has access to its trainable parameters W. Compared to conventional training, which training is done using points sampled from the clean and natural domain, adversarial training can be seen as learning using examples sampled from the adversarial example domain. Adversarial training can be even more data hungry than conventional training. Previous research has illustrated that adversarially robust generalization can be improved by having more training data and increasing the training set. Consequently, a lot of research has focused on increasing this training set. In this work, we focus on the opposite direction and try to propose methods for training robust models in settings where the training set is relatively small. So the question we are trying to answer is what can be done when we have limited data but want good, robust, and standard generalization. One of the first things that comes to mind is to do transfer learning and use a source model that is adversarially trained on a source dataset. Transfer learning by itself can be done in various ways. One possible way is to freeze all the layers except for the classification layer and essentially train a classifier on top of the frozen feature extractor. Another alternative is to fine-tune all layers on the target domain. And one can do simply something in between and only train certain deep layers. Among these different options, we would like to pick the one which results in the largest transfer of robustness. In a sense, we are trying to identify the source of robustness and find and preserve the layers that contribute the most to robustness. For identifying the important parameters, let's do a controlled experiment. Let's take a robust source model, which is adversarially trained on CFAR10, and iteratively unfreeze and train its deepest L layers on natural examples of CFAR10, the same dataset used for training the source robust model. Doing so for a wide ResNet 3210, we observe that there is a large loss of robustness even when we unfreeze relatively few deep layers. This makes us choose the first option and only retrain the classification layer on the clean examples of the target domain. In the previous slide, we mentioned that our adversarially robust transfer learning strategy is to only train the classification layer on clean examples of the target domain. However, starting from a robust source model in order to maintain robustness, instead of training on natural examples of the target domain, we can alternatively fine-tune all the layers on the adversarial examples of the target domain as proposed by Hendricks et al. Their original work focuses on improving generalization of robustness and does not focus on cases where the train set is small. However, we believe it could provide a very strong baseline for sparse data regimes as well. To compare the two approaches, let's look at the case where we start from a robust source ImageNet model and we want to transfer to CFAR100. In our case, we only are going to train the last layer, the classification layer, on natural examples from CFAR100. In the other case, we would like to fine-tune all the layers on adversarial examples from CFAR100, or in other words, we would like to do adversarial training to fine-tune all layers. Now we want to look at different regimes of data availability. CFAR100 in its general form has 100 classes, and per each class there are 500 training examples. But we want to focus on the regimes or areas where we have limited number of training examples per class. So we solve different problems for which there are different number of examples per class. For example, this column corresponds to the case where we have 5 examples per class. This column corresponds to the case where we have 10 examples per class. And we go all the way up to 250 examples per class. And we look at different metrics, the standard accuracy, which is the accuracy on clean examples on CFAR100, on the validation set, and also robustness, which is the accuracy on the adversarial examples built for the validation set. We note that in these regimes where we have very limited number of training examples per class, our technique, which is the blue bar, outperforms fine-tuning on adversarial examples on the target domain. Interestingly enough, we observe that while in our approach we train on natural examples, our standard validation accuracy isn't really high, especially for us where we use a robust source model instead of a naturally trained source model. For example, here we see a 10% gap. In hindsight, this underperformance in standard accuracy shouldn't be too shocking, given that the number of trainable parameters of our approach is relatively small. Remember, we froze all parameters except for the final fully connected layer on purpose to maximize the transfer of robustness. Given this observation, we wonder whether it is possible to improve the standard accuracy without hurting robustness. We propose a simple yet effective approach for reaching our goal of improving standard accuracy. The key idea here is to use a learning without forgetting kind of loss, which allows us to fine-tune all parameters, but at the same time keep the robust feature extractors relatively intact. This can be seen as training with an extra regularizer, which enforces the activations of the penultimate layer to not change too much, and therefore allows robustness to transfer the most. We can see here that with the right amount of regularization, we are able to improve the standard accuracy by about 7% without hurting the robustness too much. Having a large penalty and regularizing too much helps us maintain more robustness. However, it does not help us improve our standard accuracy. Thank you very much for your attention. We are hopeful this work opens many possibilities for research on robustness under data sparsity. Thanks again. Goodbye.